All right, welcome everyone. Today we're going to look at substitution rule for definite integrals. It's going to be very similar to what we've seen so far for indefinite integrals. Really the only difference is we're going to evaluate at the end. So let's get into it. And there's really two ways we can go about this, but they all come down to how we handle the limits of integration. So the first method is we're going to change the limits of integration from x to u. And we'll do that right away when we're in the process of choosing u and calculating du. The benefit of doing that is if we do change the limits of integration from x to u, we don't have to convert our antiderivative back to x. The second option, method 2, is this is sort of the do nothing method. This is where we keep our limits of integration the same. We do not change them, so they're going to stay in terms of x. And kind of the benefit of this method is the flow of it, the process of it feels exactly like what we've been doing for indefinite integrals. We get our antiderivative back in terms of x, and then we evaluate. So, whichever option you go with, perfectly fine. You'll end up with the same answer at the end. For the most part, that's about the same amount of work. Method 1 might be a little cleaner when you write it up, but either option is perfectly fine. So let's try an example, and we're going to do it using both methods to see what they look like. So let's try example 1. We're going to integrate the function 2x times x squared plus 1 raised to the power 5, and we're going to integrate this over the interval from 0 to 1. So we're doing a definite integral here. And let's use method 1 here. So this is where we're going to convert our limits of integration into u. All right, so let's see how this looks. So first we need to decide on the substitution. So that's still going to be the same. So step 1, we still want to decide on what to pick for u. Now, when we look at this, see a nice set of parentheses, see x squared plus 1 inside that parentheses. It's going to be our first choice. If it doesn't work out, then maybe we try something else. All right, so we're going to let u equal to x squared plus 1. We're going to calculate du. It's 2x. So derivative of x squared plus 1 is 2x. And then we multiply by dx. And then we want to see how these two pieces are going to fit into our integral. So if we look, the x squared plus 1 here, we know that's going to become u. And then the 2x and the dx here, we know those kind of match up very nicely with what we calculated for du. As we've seen, that doesn't always happen, but this is example 1, and everything's just working out very nice. So those together are going to give us our du at the end. All right, so we see how kind of the pieces of our function are going to fit together. Now let's actually convert the limits of integration. So this is kind of what's new. So we're just going to look at our upper limit right there, x equals 1. So that's our upper limit. And to convert this into u, we're going to plug it into our equation for u. So our equation for u is right here, x squared plus 1. That's where we're plugging into. So we're going to get u equal to 1 squared plus 1, which is 2 if we do the calculation. So our new upper limit, once we plug everything in, is going to be u equals 2. Then we want to do the same thing for our lower limit. So we look, our lower limit is x equals 0. We want to see how this fits in. So we're going to plug it into our equation for u. Again, u is equal to x squared plus 1, so we're going to get 0 squared plus 1, which is 1 if we do the calculation. All right, so we know how the function is going to fit in with this substitution. We've converted the limits of integration now, so let's go on and put all of these pieces into the integral. So we know our new upper limits are going to be 1 and our new limits are going to be 1 and 2. The upper limit is 2, the lower limit is 1. We know the x squared plus 1 raised to the power 5, that's going to become u to the power 5. And then we know the 2x dx, that matched up perfectly, that's going to become du. And that's step 2. That's our step 2 there. Putting all the pieces in. Now this time we just also converted our limits of integration, so we had a few more pieces to put in. But there we go. We have a nice definite integral now, all in terms of u. Now we just go through the motions. So let's get the antiderivative of u to the power 5. It's just a power function. So we add 1 to the exponent. So we get u to the power 6. Take that new exponent, flip it, put it in front. And there we go. We have a nice antiderivative. Then we're going to evaluate it. U equals 1 up to u equals 2. And that's step 3, getting the antiderivative. Now notice that since we're doing a definite integral, just kind of mention this, we don't need to use that plus c for definite integrals. It ends up getting canceled out. I mean, you can put it in there, but it'll end up getting canceled out. So it's easier just not to include it. All right, so we have our definite integral. We've converted it all into u. We found our antiderivative. Now the last step is to just evaluate. So how do we do the evaluation of our definite integral? Well, we plug the top number in first. So we get 1 over 6 times 2 to the power 6. Then we subtract, and then we're going to plug in our lower limit. So that's 1. So we're going to plug 1 in, and we get 1 over 6 times 1 to the power 6. And there we go. That's our antiderivative, or that's the value of our definite integral. And maybe the only thing to clean up there, we can simplify a little bit. We don't have to go overboard trying to simplify this thing, but let's do the easy stuff. 1 to the power 6, that's just 1. So if we factored out a 1 over 6, we would have 2 to the power 6 minus 1. I mean, you can go further too, but we'll stop there. And that's step 4. Just do the evaluation at the end. All right, so that's how to do a definite integral for substitution rule where we convert the limits of integration. Let's try this one again, but we're going to use method 2 where we just kind of stick with our usual routine for substitution rule. We'll get our antiderivative back to x, and then we'll just evaluate that. We'll get the exact same answer, see which one you like, and that's the method you should use. All right, so let's try this one again. Exact same example. All right, so we already know what we picked for u. So normally we wouldn't have all of this figured out already, but we know we're going to pick u equal to x squared plus 1, and du we know is going to be 2x dx. We calculated that before, so this is all the same. And we're not going to change our limits of integration. So like before, we know the x squared plus 1 raised to the power 5. We know that is going to become u to the power 5. And then the 2x and the dx, those matched up nicely, very nicely with what we calculated for du. So just like before, those are going to become our du. If we put those together. And so the actual conversion of our function that we're integrating is going to be exactly the same whichever method you use. So this is what we're calling method 2. Again, whichever one you want to use is perfectly fine. All right, so let's plug in all of our pieces. So we know that x squared plus 1 raised to the power 5, that's going to become u to the power 5. And then the 2x and the dx are going to kind of merge to form our du there. And the only thing that's going to be different now is we're going to leave our limits of integration in terms of x. And so to really distinguish what we're doing, we're going to write this in the form x equals 0 and x equals 1. Just so we remember that we haven't changed the limits of integration. They're still in terms of x. So this is an important note. If you're going to use method 2, we want to use this x equals notation for our limits. If you don't, then it looks like you may have converted them into u. So we want to be super clear what we're doing. So if we're not gonna switch our limits of integration, we're gonna write x equals for both of them. All right, so that's really the only difference here. So we have the function we're finding the antiderivative of now all in terms of u. So that's really step 2. Then we kind of go through the motions. So we find the antiderivative. Again, that's just 1 over 6 u to the power 6. We're going to evaluate from x equals 0 to x equals 1. Oops. And that was step 3. So finding the antiderivative, just like usual. Now, in step 4, for our normal indefinite integrals, we would convert this antiderivative back to x. So that's exactly what we're going to do. So we're going to convert this back to x. So wherever I see a u up in my antiderivative here, I know what u is. It's x squared plus 1. So I'm going to switch that back to x squared plus 1. So our antiderivative, if we get it all the way back to x, is 1 over 6 times x squared plus 1 raised to the power 6. And then we're going to evaluate this from x equals 0 to x equals 1. Why do they keep disappearing? And then that's step 4. All right, hopefully they don't disappear anymore. And now all we have to do is plug in, evaluate. So that's the last part of this. Plug in and evaluate to get our definite integral. And if we do that, we get 1 over 6 times 1 squared plus 1 raised to the power 6. You can probably do some of that arithmetic in your head. Subtract, plug in the lower limit, 0 squared plus 1 raised to the power 6. Again, you could probably do some of that in your head. And clean up as you want. So we have 1 over 6, 2 to the power 6, minus 1 over 6. And then we end up with 1 to the power 6. And that's the exact same answer that we found in the first part. I mean, we could go a little further and try simplifying that to make it match up exactly with what we found. But that's fine. So really, if we just compare it, it's really the same amount of work. We're just kind of doing things in a slightly different order. So whichever one you want, perfectly fine. Whichever one you like better, use that one. So really the only difference here is we converted our limits of integration first, and then we didn't have to convert our antiderivative back to x. We just could plug in right into our antiderivative as it was in terms of u. In method 2, we just kind of skipped over the conversion of our limits of integration, but then the only thing that was new here was in step 4, we had to get our antiderivative back to x. It's the only difference. So whichever one you like better, that's the method you should use. All right, let's try another one. Let's look at example 2. So here we're going to do the integral from 1 to 2 of the function 1 over 3 minus 5x squared. So before we even start worrying about any antiderivatives here, let's rewrite this function with a negative exponent. We want to write this as a power function. So I would write this as 3 minus 5x raised to the negative 2 dx. So that's just one of our kind of usual strategies here. We use negative exponents if we see fractions a lot of times. And then you could just take that dx off the top, just kind of stick it on the end there. All right, so we now have the integral of 3 minus 5x raised to the negative 2 from x equals 1 up to x equals 2. We see a nice set of parentheses, so we know what we're going to pick for u. U is going to equal what's inside those parentheses, 3 minus 5x. We calculate du. So derivative of 3 minus 5x is negative 5 times dx. Now we kind of see how our pieces fit in with what's up there in our integral. So we have 3 minus 5x raised to the negative 2. We know that piece is going to become u raised to the negative 2. And then the only thing that we have left to work with there is the dx. And in what we calculated for du, we only have a dx, but we also have a negative 5. So we have this extra constant that we have to worry about. And we know what to do with those. It doesn't show up in the original integral, so we move it to the other side. So we're going to solve for dx. And when we do that, we get negative 1 over 5 du is equal to dx. And there we go. All right, so we have all of the pieces that we need for converting our function into all in terms of u. Now we just need to decide how we want to do this. Do we want to use method 1? Do we want to use method 2? Do we want to, convert our limits of integration? I think for this one, what do I feel like doing? Oh, let's use method 2 for this one. We'll do method 2 for method 1 for the other one. So it doesn't matter. Either method, whichever one you like, is the one to do. Which one did I say? Let's do method 2. So we're going to leave our limits of integration in terms of x. All right, so now let's just plug in our pieces. So we know that dx is going to become negative 1 over 5 du. And let's write this out. So let's take that negative 1 over 5, though. Instead of having it inside our integral, it's a constant multiple, so let's put it in front. And then we'll have the integral from x equals 1 to x equals 2 of u raised to the negative 2 du. So we're just leaving our limits of integration in terms of x. So that's step 2 there, plugging all our pieces in. Now we have an integral to calculate our functions all in terms of u, our differentials in terms of u. So now we just find the antiderivative. So that's step 3. So this is just power rule. So we end up with the negative 1 over 5 in front And then using power rule, we end up with negative u to the negative 1. And then we're going to evaluate this from x equals 1 to x equals 2. So there we go. We have our antiderivative all in terms of u. Now, in order to, we didn't change our limits of integration, so they're still in terms of u, or they're still in terms of x, so we have to convert our antiderivative back to x. So let's convert our antiderivative. And while we're at it, let's kind of clean it up a little bit. So the double negative there will become a positive. And then instead of u to the minus 1, let's write that as a fraction, so it'll be 1 over u. And that way we can combine these into just one fraction. It'll be 1 over 5 times u. And then we're going to evaluate that from x equals 1 to x equals 2. So we just simplified a little bit. Now let's convert back to x. So we end up with 5 times 3 minus 5x. And we're going to evaluate that from x equals 1 to x equals 2. All right, so we have our antiderivative all in terms of x now. We left our limits of integration in terms of x. Now we're ready to plug in. And that's the last step. Just evaluate this. So when we evaluate, top number goes in first. So we're going to plug the 2 in first. And when you do this, it kind of helps to just make a nice big set of parentheses. Everything you're plugging in for 2 goes into there. Then you're going to subtract, and then everything that you plug in for 1 is going to go into the second set. So let's see what happens when we plug in 2. We get 1 over 5. And then when we plug 2 into that 3 minus 5x, we're going to end up with, well, negative 7. Right? Yeah. And then we plug the lower number in, x equals 1. We plug it in. We get 1 over 5. And then times 3 minus 5, which is negative 2. And there we go. We've evaluated this definite integral. And, that's fine. We can stop there. Maybe clean it up a little bit. We could try simplifying it a little bit. What does this become? It becomes negative 1 over 35 plus 1 over 10. Good enough. All right, so that's example 2, where we left the limits of integration in terms of x, and the only thing important there that we needed to remember is we needed to convert the antiderivative back to x. So if you're going to go method 2, it's fine. Leave the limits of integration in terms of x. You just need to remember you need to convert that antiderivative back to x. All right. You could try it out. In the lecture notes, I have both methods worked out, so you could try method 1 if you want. Might be good practice. You'll get the same answer. Let's try one more of these. Let's try example 3. We're going to do the definite integral of x over square root 2x plus 1, where we're integrating from 0 to 4. And let's use method 1. Doesn't matter. You'll get the same answer. But just to see method 1 in action here, let's do that one. So we're going to convert the limits of integration once we get to that part. All right, so before we go anywhere, we see a fraction, we see a square root. Let's rewrite that as a power function. So before we do anything, we're going to rewrite this as a power function. So instead of having a fraction with the square root in the denominator, we can write that as 2x plus 1 raised to the negative 1/2. Just easier to work with it written as a power function. And then we're going from 0 to 4. All right, so again, that's just the first little thing here. Just rewrite it. All right. So now we need to decide, we're going to do substitution rule. This isn't one of our basic integrals that we can just do. So we need to choose a u. That's always going to be step one. Again, we see a complicated term right here, much more complicated than the x. And we see a nice set of parentheses there. That's how we're going to pick u. So we're going to let u equal the 2x plus 1, what's inside the parentheses. Again, u is the inner function. All right, so we've chosen u. Now we want to calculate du. So derivative of 2x plus 1 is 2. Multiply by dx there. And then we're going to also convert the limits of integration. So let's kind of do that. So our upper limit was x equals 4. Our lower limit was x equals 0. Let's plug those into our equation for u and just see how those switch over. So we get u equal to, 2 times 4 plus 1, which is 9. And u equal to 2 times 0 plus 1, which is 1. So our new limits, once we convert everything, our new upper limit is going to be 9, and our new lower limit is going to be 1. Okay, so let's go back to see how everything's going to fit in terms of our function. So we have that 2x plus 1 raised to the negative 1/2 right up here. We know that is going to become our u, and it'll be u raised to the negative 1/2. Now let's compare the leftover terms in our integral, the x dx, and we're going to compare them to what we actually calculated for du, and we see that there's sort of a disconnect here. The only thing they have in common is the dx. So that's what we're going to solve for, is that dx term right there. So that 2 is an extra constant, so what are we going to do? We're going to solve for dx, so we're going to move the 2 to the other side. So it's going to become 1/2 du is equal to dx. All right, so going up here, we know what's going to happen to that dx term. That's going to become 1/2 du. And so the question is, what's going to happen to that x term that's kind of still there? We need to do something with that. And if we have x terms that are left over, if we've gone through and converted all of the obvious pieces into u terms, we've converted our differential, and there's still some x's left over, well, then we want to go back to our equation for u and see if we can solve that for x. And that's exactly what we're going to do. We're going to solve that for x. And if we do that, we get x is equal to u minus 1 over 2. So subtract 1 from both sides and then divide by 2. And that's exactly what's going to get plugged in right there in the middle, right where that x is. So let's put all of the pieces. So we have all these pieces that we were just building up. Let's put them all in. So our new limits of integration, what are they going to be? 1 is our lower limit, 9 is our upper limit. We know that 2x plus 1 raised to the negative 1/2, that's going to become u raised to the negative 1/2. That x term there is going to become what? U minus 1 over 2. And then our differential dx, we need to convert that as well. That's going to become 1/2 times du. And now we have an integral that's all in terms of u. So we can maybe simplify this down a little bit, but then we'll be able to go through the integration like usual. All right, so what can we do? Well, both of those have a 1/2. We see some 1/2s there, so maybe let's get the 1/2s in front. So those will combine to give us 1/4. And then we also have this u raised to the negative 1/2, and we have u minus 1 there, and we can distribute. So right now we have multiplication between u terms. We can't integrate over multiplication. We haven't seen how to do that yet. So in order to work with this, we need to actually multiply our function out. So we're going to multiply. We're going to take that u to the negative 1/2. We're going to multiply it to the u. We're going to distribute it then also to the negative 1. So what we're doing here, trying to do a few steps all at once, we're taking this 1/2 and this 1/2, multiplying those together and putting a 1/4 out front. And then we're going to have the integral 1 to 9. And then if we multiply that u to the negative 1/2 through, we're going to end up with u to the positive 1/2. So that's u to the negative 1/2 times u, minus, and then the u to the negative 1/2 times that minus 1 is going to give us minus u to the negative 1/2. So we had to multiply that out in order to get it in the form that something we can integrate now. So it's just a couple power functions, and we know how to handle power functions. All right, so that, going back to here, conversion, that was step 2. Now step 3, we're going to actually do the integration. So let's find the antiderivatives. So for that first one, for this u to the negative 1/2, we're going to do power rule. So our variable is u. We add 1 to the exponent, bumps us up to 3/2. Take that new exponent, flip it, put it in front, so 2/3. Then we subtract. For the next power function, our variable is u. We add 1 to the exponent. That takes us up to 1/2. Take that new exponent, flip it, put it in front. So a 2 is going to go in front there. And then we're going to evaluate this from u equals 1 to u equals 9. And then we plug in. All right, so getting a little tight for room here. Let's see how we can simplify this. I'm going to take this. See if I can copy this. No. All right. Wanted to move it to another page. Well, let's just plug in. So we're going to plug in the top number, plug in the bottom number, and subtract. All right, so what do we get when we plug in the top number? Well, we're going to get 1/4. And, let's, 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2. And there we go. Then we subtract. Now we plug in the lower limit. So we get 1/4, 2/3, and then 1 raised to the 3/2 power is just 1. So I won't write that. And then minus 2 times 1 to the 1/2 power, and power of 1 there is just 1. So we won't write that. So there we go. We have the value of our definite integral now. We plug the top number into our antiderivative first, plug the bottom limit into our antiderivative second, and subtracted. We could clean that up a little bit, but that's perfectly fine. So we got our antiderivative, and then we evaluated in step 4. And so the key thing here with method 1 is we converted our limits of integration, and kind of the upshot of doing that is once we get our antiderivative all in terms of u, we can just go right to the evaluation part. So, like I said, decide which method you like using better. That's the one you should use. You'll get the same answer either way. Really, it's about the same amount of work. So, whichever one you want to do, perfectly fine. All right, so that'll do it. That'll do it for integration using substitution rule for definite integrals. All right. Have a good rest of your day. And next time, we're going to be looking at integration by parts. So a new integration technique. All right. Bye-bye.